that we saw, we talked about some simple terms of the hanging wall, the foot wall on a fault. And when we think about faults and fault planes, the simplest way to keep track of it is if you imagine a block of material where there's a fault in it and that you've had some type of shift on that system. The hanging wall, if you literally picked it up in the field, is the fault that would be above, or the block that would be above the fault plane. Or if you look at the fault plane itself, that block would contain the base lineament, the base plane of that fault. If you look at the foot wall, that would be the block left behind on that system. So those terms can help you begin to interpret some of the geometries when we have faults that are dominantly dip slip, where we've displaced either one block up relative to the other in a contractional or a compressional setting, or we've displaced one block down relative to another in an extensional type of a system. And so we have some very simple terms that we want to keep in our arsenal. We have normal, reverse, thrust, and strike slip. Now, these are, right now, very, very simple systems, very, very simple geometries in our minds. That's going to change over the next few days because we're going to realize these systems are far more complicated. The scale of these faults can vary dramatically. We can look at normal faults on a very small scale. We can look at normal faults where the faults may have vertical offsets on the order of 10,000 meters or more, may have extensional displacements, lateral displacements on the faults that might be measured in the order of 10, 15 kilometers. So that's not something you can easily walk up to in the field and go, oh yeah, that's really cool, I see that. It's something that we have to be able to reason out in the geometry of the system. We can have faults all the way down to the crystalline scale. We can find micro faults in thin sections when we're looking at deformation regime, and we can see faults at offset of individual crystals where the offset might measure 200-300 microns in that particular system. So we see these types of geometries, these types of offsets on all scales of observation. We see them on other planets. There are faults that we have found on other planets that have kilometers and kilometers of offset. So that this is a process and a geometry that we want to become a little bit comfortable with and start thinking about those geometries and what might control these geometries in that particular system. And so last time we had started going through some slides just to sort of familiarize ourselves with what faults might look like in the field, because a lot of times faults in the field take on an incredibly different appearance than the picture-perfect things you find in your textbooks or the simple stick diagrams that are drawn in your classes. And so we want to finish up with those. I believe we stopped here last time. This is Nasty Knob, just outside of Canyon City, Colorado. We have here the Ordovician. These rocks are Ordovician Fremont. It's a dolomite. It's a late-stage dolomite, so we determined that genetic dolomite that has preserved some of the fossil content. These rocks down here are the Pennsylvanian Age Fountain Formation, and what you can see is that these two truncate up against one another, so that we have a fault that actually cuts right up through there. There's the fault plane. This is a field sledgehammer by the name of Bertha, and Bertha is a very good friend. If you're going to go to field camp, don't invest in those Estwing nice geology picks other than to put it on your bookshelf and show off. Because if you get into a situation where you're having to break these rocks apart it's going to tink, 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 tink all day, and you're never going to be able to do anything. You need a 2 to 3 pound sledgehammer. Yeah.
Okay, I'm trying to remember, but my mom had one she gave me, and it has like a pick on one
Right.
end, and then something else on the other.
That's an Estwing type of hammer. Those are very, very lightweight. You want something a bit more massive
Okay.
in order to be able to break the rocks apart, particularly if you work in igneous terrains. Now,
Doctor,
yeah.
yeah, what we found was best, when we got there, we went to the hardware store and bought sledgehammers.
Yeah.
And so we got the, it was a 2-pound sledge.
Mhm. That works great.
And then if you need to get more refined, just get yourself a chisel.
Yep,
That way you
that is by far the better way to go. Now, a lot of times faults in these geologic settings are also associated with folds or flexures. We've seen this particular outcrop before from the other side. We are up in the Bighorns. The Bighorn Basin is out here. Sheep Mountain Anticline is just over there. This is near the town of Graybull and Lowell. Graybull is actually one of the provisioning and key flight areas for wildfire prevention. They have a huge airport. It's a very small town, but it's an enormous airport where a lot of these tanking systems are kept over the seasons. We're looking here, this is the Bighorn Monocline, and you can see as we look off towards the south, towards Shell Canyon, we have this bend in the rocks. Well, that is rooted by a fault, where what happened in that particular system was we have this type of an offset and a reverse fault in the heart of that particular flexure. And so in this particular case, that fault expresses right there, and we're standing on it where we are to take this particular photograph. And in this area, what happened is that this completely broke free in a thrust and overturned the entire section. And you've seen that image before where those are overturned. Now, if we go to that, this is the Five Springs thrust. In the previous picture, we had gone up here and then hiked up to an area over in there. And so this is the material that has completely overturned, where that thrust broke through and took this material all the way over in a now high angle thrust that bends outward into the system. And so if you remember, we have the Laramie Formation, Goose Egg, we have the Amsden, the Ten Sleep, and then on up into, or we're going down section into the Madison up here. So this has been completely turned upside down along a fault, along a thrust fault in that particular system. Now, thrust faults can take on all types of different appearances. This is the Grovant range and that particular fault. This is near Hoback Junction in Wyoming, just to the south of Jackson, Wyoming, and it has a bend. See this bend right here? This is part of the fault, and the fault plane itself is right there. And so that immediately starts to mess up some of our geometry, because instead of being a nice straight line, what we see is that the fault plane bends. And so in answer of an earlier question you had, that would be a mode 2 propagation of that particular type of failure in that system. So this is what a large scale thrust might begin to look like. We have an example here. We've jumped up to, the nearest town is Bad, Montana. This is just outside of Glacier National Park. It's a wonderful place to visit, and it's a beautiful place to do structural geology as well as glacial, because we have thrust faults. This is the Chief Mountain Klippa, And a clip up is an erosional remnant, so that there was a massive thrust fault system coming through here and it's been eroded away, leaving only this remnant here. And this particular photograph is actually looking toward here on the outcrop. So our view is more oblique to this outcrop. So this face is that collapse right in there. The roof here, thrust of this complex is right in here. And you can see it beautifully exposed. That's a thrust fault. There's another thrust fault that comes up through here. And so this is part of a thrust system. This is part of a duplex that we need to learn about that geometry, but it's beautifully exposed in the field. Now this is in the Blackfoot Nation, and the Blackfoot Nation holds this as being a highly significant site for religious purposes. So it's a very spiritual site, and they really don't want people back in there to desecrate that particular site. So this group of geologists was very lucky to be able to get in there and do work on that particular feature. Now, we've jumped, we're down here. This is what, Two Medicines Lake here. This is Senepaw Peak, and you can see a thrust fault right through there in that system, and another one coming in and climbing again, curving in that particular system. And so this is Senepaw, really nice place to go hiking around that system. And now we've gone, this is Mount Crandall. We are in Alberta, Canada here. We are right at Prince of Wales Lodge, which is, the Prince of Wales is just off behind us here. Mount Crandall is part of a type of structure we're going to call an antiformal duplex. Part of a thrust fault system. You can see where the rocks come in, bend. Over here, they come down, and then they're cut off in here, and our field of view from there to there is that mountain. So this is a relatively large-scale complex in that thrust fault system. And so Mount Crandall is a classic example of a type of feature we're going to learn to call an antiformal duplex. Beautifully exposed. You can walk all the way around it to get an idea of the size that these features can take on. This is a very, very small part of a massive thrust fault system, where that thrust fault system has an overall expression that exceeds 200 kilometers across, and the offsets are enormous. Yeah.
Do you have any examples from Mexico?
Not in Mexico.
No.
None of that.
Dangerous, right?
None of that system. I haven't been to that system.
You haven't been there, okay. So it's a different system down there.
In Mexico, yes.
Oh, okay.
Dr. Tapp, would that have been the example of an overburden that's been overthrusted?
Well, that is a duplex feature, so it was relatively deep within the structure.
Okay.
And it is a system where there was sufficient, let me put it simply, there was sufficient energy in the system that the individual thrust blocks overrode each other and stacked up into an antiformal structure. So this is another example of what a thrust fault system looks like. We're in the area of Two Medicines Lake here again, and that dashed line is the Lewis thrust. On top of that, we have Precambrian aged materials, mostly non-metamorphic, which is kind of intriguing. And below, we have Cretaceous age materials. And so we've put older materials on top of younger materials.
And all the pictures you've shown, they're mainly thrust faults, right?
Well, so we've seen a variety of different faults as we progress through. because this was slide, what, 36 of that set. So we've seen a lot of different styles of faults. Yeah.
We're going to, you said we'd get into more anti-formal duplex
Oh, yeah.
formations later. Are you going to describe what they are in more detail then?
Yes,
Or- okay.
absolutely. Here's another shot of the Lewis thrust. Again, these things are often not that easy to see. And in this particular case, someone was nice enough to put a yellow line dashed for us to photograph in the field so we could see the break in that particular system. So these materials out here are Cretaceous aged sediments with glacial till, Pleistocene material on top, and then these are Precambrian aged materials all up in here. And the thrust fault just goes right through there, over there, and then at the base of that little range there.
So it was overturned. What is that?
The Lewis thrust is part of the, how to best put this? It's part of the Cordilleran system. It's part of the Rocky Mountain Cordilleran system where we shift from thicker skin deformation style into thinner skin deformation style. And it has displaced Precambrian materials on top of Cretaceous age materials. And so the root of the complex would be back here about 150, a little over 150 kilometers from where we are now. So it's part of that thin skin style of deformation in the northern Cordillera. Okay?
I'm just curious, have you covered the difference between thick skin and thin skin?
Not yet.
Oh,
No. We're just taking a cruise
oh, okay.
right now.
Get those hydraulics.
But he's had field camp, so he knows. So here's another example. This is another example of what a thrust fault looks like. This is Running Eagle Falls, or sometimes it's called Trick Falls, because there's a waterfall in here, behind and underneath the waterfall there.
So is it like a river stream or something that flows underneath the rock?
Then what happens is there is a breakthrough into a cave back here. It's about 200 meters back upstream. So a lot of the stream is diverted down through a cave and comes out in this waterfall. During wet season, this waterfall will run. During dry season, it'll have no water and all the water will be down there. So that is Running Eagle Falls. It's a lovely, lovely place to go hiking. Watch out for the black bears there.
Well, black bears are usually not that dangerous.
They can be. We've run into a couple that were
In Michigan.
had cubs. They were
Yeah.
unfriendly. When we look at this system, what do you see?
Oh, you see those?
Yeah.
Yeah, there's a displacement along this plane right there. So that shifted from there to there. That is a very small scale displacement. You can see the Brunton compass and the pencil for scale, but it gives us a type of offset. Is that right or left lateral?
Left lateral.
Not.
Well, you say it's left lateral in the picture, sir.
Oh, I gave it away.
Yes, sir.
What's the evidence of left lateral?
If you're standing on the bottom portion in regards to the picture, it's the portion away from you zooming.
Doesn't
Yeah,
matter
that
which
looks like it
direction.
has shifted to the left.
Yeah.
If we stand up here, this looks like it has shifted relative to the left. This is a very small scale offset on a much larger fault plane. This is in the Ouachita Valley Fault Zone. The overall offset in the Ouachita Valley Fault Zone is on the order of about 120 kilometers of offset. So this is just itty bitty compared to the overall offsets that we see in that particular system. So when we're looking at faults, we often see smaller scale exposure giving us information about the larger scale. We can have faults like this. San Andreas is a, would that be right lateral or left lateral? Oh, okay.
Why?
Well, you can still see it. This is a right lateral system where the total offset on that system is on the order of about 600 kilometers of offset. This is one of the major strike-slip fault systems in the world. Other ones would be the Anatolian system in Turkey, which has produced some significant faults. The Izmit quake is the most recent devastating fault or earthquake that occurred. The Alpine fault system in New Zealand, the Tanshan fault system in China. Tanshan is actually one of the most dangerous fault systems in the world. The last major earthquake that occurred in the Tanshan system was 1976, and over 200,000 people perished. As an estimate, probably closer to 750,000 individuals perished in that particular earthquake. So these systems here, strike-slip systems, can be destructive. It does not take a significant amount of displacement or a significant magnitude in a strike-slip system to cause significant damage and loss of life. If you think about what would have occurred a few years ago, we had a massive 7.5, it wasn't massive, but a 7.5 earthquake just outside of Port-au-Prince, and death toll on that is on the order of 230,000 people perished from that one earthquake in that system. So these things can be significantly damaging in active systems.
Dr. Cap,
Yeah.
The nuclear disaster over in Japan, Fukushima, was it built on a?
It was in the proximity of that entire system is a subduction zone in that system, and so that geology would be a type of thrust displacement where you have the Pacific plate descending at a relatively shallow angle, and now we're going to put Japan up here. And what happened was that in this particular case, this is what we would describe as a megathrust earthquake. And so what happened was the Pacific plate had been displacing at a normal rate, but it was not slipping, if that makes any sense. It was locked here. And so what happened, the easiest way to think about it, is this is the Pacific plate, this is Japan. So we're going to put Japan on top of the Pacific plate, and now we're going to displace the Pacific plate. What happens? Japan distorts, it deforms as this continues to move. At some point it breaks, and it can displace relatively fast. The overall offset was on the order of 35 meters of offset back in the worst part of that particular earthquake system, and that offset occurred in about a second. So it produced a very large magnitude earthquake. In that particular earthquake, we were astonishingly lucky that it wasn't a larger magnitude, because if you look at the inversion data from that to image out the fault plane and the displacement, when you look at those data from University of Tokyo and from the Japan seismology group, the fault, or the earthquake began, it then arrested, shifted slightly to the south, and then finished off. If the entire system had slipped at one time, we would have been looking at a magnitude around 9.7, which would have been bad. It was bad enough as it was, but that could have been a far, far worse. And if we go back to the Sumatra quake, the Boxing Day earthquake, again, that was a megathrust, and in that particular system, hundreds of thousands of people perished because of the tsunami after that followed that particular earthquake. So these things can be quite devastating in that system. And what happened here was the nuclear reactor at Fukushima was south of the actual slip zone, but there was enough damage, and then the tsunami came in that kind of wiped out the system, and they were not really equipped to handle that type of disruption. Now, faults can be tough to recognize. This is the San Andreas. Do you see it? It's not the canal. Yeah, right there. Cutting through the Imperial Valley, cutting through an agricultural system, and you can even see a very small offset in the canal in there. So the appearance, the surface appearance of these faults, the actual scarp that will form, can be deceptively small. This has about 600 kilometers of offset, except what we're seeing here is offset of man-made features. And so those are going to be relatively small, whereas the geologic offset can be quite large in that particular system. So these faults can be intriguing. If we go back and look at the Ouachita Valley Fault, that's this feature right through there. And let's see, nope. Where we were before was down right about there on the Ouachita Valley Fault. It's a little bit of complicated fault zone, some intriguing things, and we're going to go play with it. We're going to go down and put our hands on the fault. This is one of the areas that you can do it. Do you see it? Massive, massive, huge strike slip fault. Where is it?
Down.
Oh, there you got it?
One there.
Right here?
Yes.
So the fault itself cuts right through here, right through there. This material over here is the Ordovician Cool Creek Formation, and it's actually a pretty cool formation, for a pun. This is the Pennsylvanian Collins Ranch conglomerate over here. There's the fault. A lot of times they do not express as these very nice stick diagrams that you have in class. So faults can be wonderfully complex. They can produce some intriguing structures. This is in a strike slip fault zone here. This is a place called Limestone Hills because, well, there are hills and they're made of limestone. Geologists get pretty literal sometimes. Do you see any faults? Who wants to come up to the board and point out a fault? Tim does.
You're welcome, Tim.
Thanks, John. We can always count on you. I think right there.
Yes, exactly. Is there another?
Another one that cuts it, that goes like this.
Let's think about that. Who wants to take a guess? Maybe Mariah, any of you guys want to take a guess?
Is there
Yeah, I
another
think one on the top.
parallel?
Right there.
No.
There's a fault that comes up, comes over and joins.
Well, I guess it doesn't.
A fault that cuts right through there. So Tim got this one, Libby got that one. These two join exactly as you described, Steve. This one comes around and they join back together again. So this is a strike slip fault, and you would have to describe that fault as having both strike slip and thrust characteristics. And as you walk around in Limestone Hills, it's a beautiful place to map. As you walk around in Limestone Hills, you realize that there are normal faults, there are strike slip faults, there are thrust faults, there are reverse faults. So it is kind of an all the above situation. So faults can be a little bit difficult to work with. I'm going to do the lights, so don't scream. and we can have a great deal of variation. The expression can be at times quite challenging to come up with. And so we need to discuss a relatively simple concept, couple of concepts, and we want to think about how they might express in a real-world setting. Now, the concepts that we want to think about are the concepts of slip versus separation. And they have very different meanings. The concept of slip is, what are you doing? Go away. When we think about slip on a fault system, we can describe slip when we know the absolute or the true displacement. So here, we have the absolute displacement on the fault. We know exactly the vector of displacement, and we can describe the components of that displacement. So in slip, we can imagine, if you will, we're going to have a fault plane here. Oops, that's bad. Okay. So we have a block. Imagine, if you will, the upper block here is there but invisible. Okay? So we're going to displace this upper block down and a little bit to the side. So, and again, imagine, if you will, that we had a way of taking a laser and drilling through the two blocks prior to the displacement, so that we would have a point on the lower block and a point on the upper block that we could connect. So that we have here, this would be the point on the lower block, that would be the point on the upper block. Are we good? So I can talk about that vector in the plane, and that is going to be a net slip. I can talk about a dip slip and a strike slip component of that displacement in the plane itself, in that dipping plane. Okay? This is the case where we can measure accurately the sense of displacement. So the net slip is simply the vector that connects those 2 points. The dip slip is the down dip portion of that on a fault surface. The strike slip is the strike component of that, again, on that fault surface. If I want to, I could come out and talk about a component that is horizontal, or I can talk about a map component, and I can talk about a vertical component of that. And so it might help if we have a fault plane, and we just happen to have a handy-dandy fault plane here in class. It's amazing what these podia can be. So if I have a point and a point, The upper block point is here. This is where it's offset from. That is the net slip. My dip slip would be down, my strike slip would be over. If I come up here, this would be my horizontal slip. That would be my vertical slip. Just a bunch of triangles. Okay, are we good? That's if we have a point that has been offset. When we don't have the absolute offset, but we end up with an apparent we use the term separation. And the analogy that we might use is, let's say that there is a dike that was cutting through the area and has been offset. So that on the block here, the dike looks like that. On the footwall, on the hanging wall, the dike is offset over there. Okay? Can we determine the offset? Can we make a determination of the absolute offset? Who wants to hazard a guess? To help out, you're going here. No, we can't. Because we could have a pure strike slip system here. Absolutely only strike slip. Or I could have almost any infinite number of potential dip slip components as well. It could have offset exactly that way, or down, or down, or down, or down, or down, or up, or up, or up. We really can't determine what the true displacement is. And so we're going to use the terms separation, where we have an apparent offset, and then we enumerate. This would be the slip separation that we see. If this was a stratigraphic unit, we would talk about the stratigraphic separation or the horizontal separation in a system. So when we can't enumerate, we're going to call it separation. When we can, we're going to call it slip. And geologists will actually work very hard to be able to determine if they can actually measure the true displacement. In the field, we try to find what are called nick points, where we can say, okay, that and that were absolutely connected, and we can determine that true displacement in the system. So we have two different concepts. The next thing we need to think about is, what role will erosion play in causing problems for an interpretation? And so we have 2 minutes left so we can have a partial puzzle. Let's say that we have a map. We've been diligently mapping in the field. We've worked very hard. We find a fault cutting right through there. This is a map view. And we find that we have this scenario where these layers are